We are Team Truxie, and this is our project for the AEP track SmartLine Guardian. Our project demonstrates how real-time monitoring and predictive modeling can identify when a transmission line moves from a safe state to a stressed or overloaded condition before serious damage occurs. Most transmission lines today are still operated by using static ratings. These ratings assume worst-case environmental conditions and rarely adjust as conditions change. In reality, factors such as temperature, airflow, and load fluctuate constantly. As current increases, the conductor heats up. When it heats up, the meadow expands, which increases sag and reduces ground clearance. If the conductor remains above its maximum temperature limit for too long, the material can weaken and become unsafe. Utilities therefore need systems that monitor changing conditions dynamically instead of relying on fixed assumptions.
SmartLine Guardian is a real-time power line monitoring system designed to estimate how stressed a conductor is under changing conditions. Our system continuously measures the current flowing through the line, conductor temperature, and environmental conditions such as temperature and humidity. Using these inputs, our algorithm estimates thermal expansion and calculates the predicted sag of the conductor. This allows the system to detect when a line transitions from safe to stressed and ultimately to an overload condition, giving operators an early warning before failure occurs. Our prototype is built around an ESP32 microcontroller, which collects and processes sensor data in real time. A thermistor attached to the nichrome wire measures the conductor temperature, while a DHT11 sensor measures environmental temperature and humidity. All this information is sent to a software dashboard, which displays conductor temperature, load, the calculated safe operating limit, predicted sag, and system status. To simulate a real transmission line, we use nichrome wire powered through a buck converter, allowing us to control the current and reproduce heating behavior. We also attached a weighted object to the wire to better simulate the mechanical load of a real transmission span. Here are some parts that we use throughout our project.
Right now, the conductor is operating in a safe state. The current is low, the wire temperature is stable, and the estimated sag remains within a normal range. Based on these conditions, the system classifies the line as safe. But as we increase current through the wire, resistive heating causes the conductor temperature to rise. The thermistor detects this temperature increase and sends the data to the ESP32 in real time, and our algorithm then recalculates the predicted sag based on the higher temperature and increased load. As the conductor continues heating, the system recognizes that the line is approaching its safe operating limit. The predicted sag begins to increase, and the dashboard indicates that the conductor is now entering a stress condition. This stage is important because it gives operators warning before the line reaches a dangerous state. If we continue increasing current, the conductor temperature eventually exceeds the safe threshold, and at that point, the predicted sag becomes large enough to indicate a serious thermal and clearance risk. The system then classifies the line as overloaded, triggering a visual alert. This demonstrates how real-time monitoring can help operators respond before a failure occurs. SmartLine Guardian shows how utilities can move beyond static line ratings and instead rely on live environmental data to understand line health. By combining load measurements, conductor temperature, and environmental conditions with a predictive sag model, the system shows not only when a line is heating up, but how severe that stress may become. During development, we incurred several challenges. For example, the thermistor initially produced unstable readings, and the DHT11 environmental sensor required multiple wiring calibration adjustments before it reported reliable data. We also had to correct several issues in the dashboard code so the interface properly displayed sensor values and updated the system status in real time. Working through these problems helped us improve both the hardware and the software components of the project. Ultimately, this type of monitoring could help utilities detect overload risk earlier, improve grid reliability, and safely increase transmission capability when conditions allow. In a full-scale deployment, each monitoring unit could include a GPS module, so utilities know the exact location of every sensor. If a line becomes stressed or overloaded, that sensor could automatically send a location-based alert to operators so they can respond immediately. Thank you.